we'll move on to our next invited talk by Chelsea Finn. Chelsea Finn is an assistant professor in the computer science and electrical engineering at Stanford University and co-founder of her startup, Physical Intelligence. Her research lies in the ability to enable robots and other agents to develop broadly intelligent behavior through learning and interaction. Her startup focuses on bringing general purpose AI into the physical world and is developing foundation models and learning algorithms to power the robots of today. She has made foundational contributions to meta learning, robot control, and development of generalist agents. She'll be presenting on the topic, the ingredients of scaling robot reinforcement learning. Yeah, all to you.
Great. Thank you for the introduction. Sad I wasn't able to make it in person today, but yeah, excited to share some of our research, and there should be plenty of time for questions. So at the end, so please feel free to think about questions that you have as I go through this. So to set the stage for what I'm going to talk about, I'm really excited about how to develop intelligent robots, and I think that we've seen a lot of really exciting advances in robot foundation models specifically. So far, what this looks like is it looks like constructing a demonstration data set across a lot of robots, perhaps some other internet data, and training a large transformer-based model to predict actions through imitation learning. And we've seen some pretty cool results from this. I'll highlight a couple from Physical Intelligence on completing really challenging long horizon tasks with these large models pre-trained on diverse robot data and then fine-tuned to, for example, complete this 10-minute task of unloading and folding 5 items of clothing. And then also more recently, we saw that these models are also capable of being able to generalize to new homes they've never been in before and complete useful tasks. So as someone who loves working with robots and seeing robots do cool stuff, both of these results were really, really exciting to me. But there's also still a lot of work to do. And in particular, so far, these models are trained entirely with imitation learning. And what I'd like to talk about in this talk is how we might scale reinforcement learning to robot foundation models. Perhaps with this audience, there isn't a lot of need to motivate using reinforcement learning, but I think it's always important to ask the question why in terms of prioritizing. And one of the reasons why I'm really excited about reinforcement learning at scale for robotics is I think that we should be able to get a much higher final performance than with imitation learning. And in particular, reinforcement learning allows us to directly optimize for final performance via reward maximization rather than optimizing for matching the actions of an expert. And through online data collection from a policy rather than from a human expert, we can expand the data distribution to include states in which the policy is likely to visit, and it allows the robot to learn from its mistakes. I should mention that when I say reinforcement learning to these foundation models, I'm most excited about reinforcement learning in the real world, where the robot would actually be interacting with the real physical world and not just in simulated settings. Now, as an aside, you might be wondering, well, do we already know how to scale reinforcement learning? Like we've seen large-scale reinforcement learning for language models that's scaled to very large data sets and very large models. And so maybe we already know how to basically translate this to robotics and get really high performance on physical systems. But unfortunately, we don't quite have all the answers. So a lot of the algorithms for large-scale RL for LLMs assume that you're in a bandit setting or assume that you can do multiple rollouts from the same exact prompt. And this is really easy to do in language models where you have a prompt and you can just like sample multiple outcomes. But in any sort of interactive setting, it's really hard, especially in the physical world, to try to like reset the scene to exactly the same spot and try to look at multiple outcomes from the same state. So hard that it's really not something that I would actually consider doing in an algorithm for robotics. And likewise, robotics is typically not operating in a bandit setting. Typically, you're instead going to be operating in settings where there is the kind of very extended impact on your actions, although it could be interesting to study what bandit algorithms could do in a robotic setting. And then beyond this, there are algorithms like PPO that in principle could be applied at scale to robotics, but when you're applying them in the physical world, it's hard to get very dense reward feedback, and these algorithms can also be extremely inefficient and require tons and tons of data. And in principle, we shouldn't shy away from large amounts of data, but I think that PPO is probably kind of beyond excessive in terms of data collection. So maybe it's worth a shot, but would be very challenging to apply in the real world. And the last thing that I'll mention here is that I think we've unfortunately seen limited validation of value-based reinforcement learning methods at large scale. Generally, the language model algorithms are not deeply relying on a value function to optimize the policy. And I think that for longer horizon tasks where we're not operating in a bandit setting, learning a value function will probably be pretty important. Okay, so unfortunately, I haven't figured out how to scale RL to robot foundation models yet, but what I'd like to talk about is a couple ingredients that we've been studying to scale robot RL fine-tuning. And in particular, looking at a setting that is a little bit more practical than the fully online setting. And then second, looking at RL specifically in the context of diffusion policies and an algorithm. And these are kind of two ingredients that I think might be helpful and important steps towards scaling RL to fine-tuning foundation models. Okay, so now to set the stage for the first part, if we were to look at kind of a typical RL recipe, oftentimes what it looks like is you might collect data on by running your policy, and then update your policy using that data, and then repeat that process. Now, on-policy algorithms are going to update the policy only on the latest batch of data, and they're going to throw away a ton of previous data, and this isn't going to be great for generalization. On the flip side, this kind of motivates using off-policy algorithms that are going to reuse existing data using a replay buffer. However, one thing that's worth noting about off-policy algorithms is typically you will collect one time step of data and then take one gradient step on your policy and have a very tight loop every single time step where you're collecting a tiny bit of experience and making a tiny update to your policy. And one thing that's a little bit subtle about this kind of algorithm is that it can be pretty challenging to do this at a large scale because it means that in the loop of collecting data, you're going to need to be updating your policy. And if you have a really big model and you need to be kind of tuning hyperparameters and monitoring the loss in the loop of also collecting data, this is going to be something that's actually like really complicated and really challenging to do at a large scale where say you have robots that are kind of like, I don't know, maybe you have 10 robots that are deployed and they're all collecting data. It's going to be hard to be like asynchronously updating your policy at the same time. And something that I think is going to be easier to scale, at least in the context of robotics, is something that was an idea that kind of appeared in this paper from 2020 that's gone by a few different names, either iterated offline RL or deployment efficient RL. I'll use the term batch online RL to refer to the fact that it'll still be kind of doing online RL, but we'll be collecting larger batches of data and doing larger batches of updates rather than having like a really tight online RL loop. And in particular, the way this works is that instead of having the really tight loop, first you'll kind of collect a batch of online data collection, and then you'll add these N episodes where N is fairly large to your data set. You'll then train, you kind of run multiple training steps on the latest batch of data and then redeploy your policy. And this loop will only do a kind of a fairly small number of times. Maybe we'll do it 10 times or 20 times, but not more than that. And this is something that I think that should be this sort of kind of iterating between collecting a big batch of data and training your policy and doing that a fairly small number of times, I think will be far easier to scale, at least in my experience working with robots, than something where you have a really tight data collection loop. Now, you might wonder, okay, well, why are we talking about this? We could probably apply existing algorithms to this, but one of the things that we find is that this setting actually introduces some slightly different considerations from typical RL methods, whether they be kind of fully unconstrained online methods or fully offline methods. Cool. And so what I'll talk about next is what are those different considerations and kind of how does this picture look when we're in this sort of like larger batch online RL setting? And in particular, we'll study a few different attributes that we found to be important. So we'll study the algorithm class, how we extract the policy given a learned value function, and the degree to which policy expressivity is important. And we'll do this on 6 simulated environments before running experiments on a real robot. Lastly, to mimic conditions that I think are quite realistic in robotic settings, we will assume that we have initial demonstration data, because generally collecting some demonstrations initially is something that's not too hard, and there's already like very large demonstration data sets that exist. And we're also going to be assuming sparse rewards. And by that, I mean just like 0, 1, like did the robot succeed or did the robot fail, which also is generally not too expensive for a human to provide to the robot. And then, like I mentioned before, we'll only be doing 10 to 20 kind of loops of that, where we'll like be recollecting data. And per iteration, we'll be collecting around 200 rollouts from our policy. Okay, so this is the setting that we're operating in. And the first question that we ask is, like, when we're in this this problem setting, can we just imitate the successful policy rollouts? This is actually a really popular algorithm in the LLM world, and it's very simple. It should be, in principle, very scalable. We'll refer to this as filtered imitation learning. And when we compare a value-based RL method to filtered imitation learning, we find that generally filtered imitation learning doesn't improve very much. And generally, we see that a value-based RL method is able to provide more consistent improvement. And in 4 out of the 6 cases is kind of significantly improving over filtered imitation learning. So that's kind of the first finding that we kind of find in this setting, which is kind of a good sign. Like a value-based RL method is still applicable to this batch online RL setting where we're only running like 10 iterations or 15 iterations of recollecting data. Now, why is this the case? We find that with filtered imitation learning, the policy ends up being quite narrow, whereas with value-based RL, we see that the policy successes are a lot more diverse, which suggests that it's basically able to essentially kind of explore a little bit more in the space and yeah, get more diverse examples of how to succeed at the task. Okay, and then the other question to ask is, if we're in a batch online RL setting here, it's not too hard to potentially it's not too hard to increase the size of the batch of data, because each time you could kind of deploy your policy on the robots, collect a large batch of data, and then update your policy. And so we wanted to know, if we collect a larger batch of data with the same number of iterations, do these algorithms get better? And generally, we find that if we move from a kind of a small to a larger batch of data collection, we see that performance increases. And performance increases actually most significantly for a value-based RL method, which is also encouraging. Cool. So that was kind of the algorithm class, whether it's using imitation learning, like filtered imitation learning, or a value-based RL method. Now, let's say that we're going to learn a value function. Specifically, we'll learn a Q function. And we want to study different ways for getting a good policy from that value function. We're going to, because like you can't compare every single possible different thing, we're going to compare 2 different ways to get a policy that have been shown to be fairly successful in previous kind of fine-tuning works. The first is to use advantage-weighted regression, which is going to kind of imitate the actions, but weighted by the exponentiated advantage, and as measured by our value function. And then the second approach will be, instead of explicitly training a policy, we're actually just going to take our policy trained with imitation learning on the data and sample multiple actions from that policy and execute the actions that have the highest value according to our Q function. And so we'll refer to this as kind of an implicit policy extraction method, because we're not actually going to be explicitly trying to propagate value from our Q function to our policy. Now, somewhat interestingly, one of the things that we find that this implicit approach, despite arguably like potentially not even being that strong of a policy extraction method, we find that it's actually far more performant in this kind of batch online RL setting than using advantage-weighted regression. And in particular, if you look at kind of the performance before RL versus after RL, In purple, we see that kind of this implicit approach, which corresponds a lot to the IDQL algorithm, leads to very consistent improvements in performance, on average leading to a 34% improvement in performance, whereas with the AWR algorithm, we don't see very reliable performance improvement. Now, so generally, I guess we find that kind of implicit policy extraction is better able to leverage these batches of new online data. And then the last component here, which is really, really important, especially for an algorithm like IDQL that's sampling multiple actions and picking the best one, is the policy class. And typically, a lot of reinforcement learning methods have used Gaussian policies, but it kind of is natural to hypothesize that if we're in this more kind of batch online setting where we're deploying and collecting a lot of data before we update, that you would probably want that batch of data that you collect to be pretty diverse. And if you want it to be pretty diverse, then you probably want a fairly expressive policy that can capture like multimodality and can capture different modes of a good policy. And so here we're going to be comparing using a Gaussian-based policy versus a diffusion-based policy. And we're comparing Gaussian and diffusion for implicit policy extraction, and we'll also compare to a Gaussian policy with AWR, just to control for the fact that like perhaps this is kind of specific to implicit policy extraction. And what we find here is first that diffusion in green performs far, far better than Gaussian policies in gray and beige. And it also enables better implicit policy extraction. So I guess kind of this makes a lot of sense. First, the diffusion policy gives us more diverse data, and so it thrives in this batch online RL setting. And second, it also works better with implicit policy extraction where we're sampling multiple actions, because if you use a Gaussian policy that's very, especially one that's very narrow, if you sample multiple actions, probably you aren't going to get a lot of diversity, and you're not going to be able to actually maximize your Q value effectively. Cool. So kind of a summary of the recipe that we found to be most performant in this batch online RL setting is first you use a diffusion policy. And this is used to fit the demonstrations and to fit the ongoing data that you've collected. Second, we find that it's helpful to actually use a value-based RL method rather than simply using filtered imitation learning. And then lastly, we find that it was more effective to simply sample from that policy train with imitation learning and pick actions with the highest Q value, or this implicit policy extraction, compared to trying to kind of explicitly train a policy that kind of weighted by exponentiated advantages. Now, we took this recipe that seemed to work quite well in simulation and translated it onto a real robot. And we looked at this fairly simple task of picking up a piece of tape and hanging it on a hook. And we gave it only a fairly small number of demonstrations. And so if we do imitation learning only on the demonstrations, the robot kind of struggles to complete the task. Its overall success rate is something around like 45% success. And then after running just 3 iterations of batch online RL, we see a policy that's kind of significantly better. That's around 80% success rate. And so this is kind of a validation that this sort of recipe works well. And we also see that if we use filtered imitation learning on the data, this also kind of struggles to kind of see an improvement from the online data. Cool. So that's the kind of the first part of trying to study this like more batch online RL setting. And I think it's going to be easier to scale to large models. The second component I'd like to talk about is RL for diffusion policy. And I guess it's good to ask the question of why again, and in particular for like why should we study RL with diffusion policies? If we look at a lot of the kind of successful foundation models in the kind of the robotics field, we'll see that kind of the pi models are based on diffusion, the group model uses diffusion, and the helix model uses diffusion, while OpenVLA uses kind of an autoregressive prediction. And so generally, a lot of these models, like more and more of these models are starting to use diffusion. I also suspect that the Gemini model also uses diffusion on their robot. And so these models are like really, really effective for capturing a lot of diversity in demonstration data. And that's one of the reasons why they're being used. But it brings up the question of how we might use RL to fine-tune these models. And generally, there have been a number of methods that have looked at using value functions to fine-tune diffusion policies. And one example we saw previously is just to sample multiple things from your policy and take the best action according to your Q function. There's also approaches that try to guide the denoising process using a value function. But unfortunately, like these methods, they're leaving performance on the table. They're not like actually updating the weights of the policy with respect to maximum value. And that means that they probably aren't like fully optimizing the Q function. Now, there's also approaches that try to directly backpropagate value through the diffusion process into the policy weights. And so in principle, this is like kind of the obvious way to try to kind of more directly maximize value with your policy. But unfortunately, these approaches can be unstable. And as a result, they also don't work quite as reliably. And so motivated by the fact that these methods aren't performing super well, we wanted to introduce a couple key ideas for addressing these challenges. So the first is that instead of trying to directly, we'll be operating in a kind of a fine-tuning setting. Again, we'll have an offline data set of demonstrations to mimic what we think we'll see in large-scale kind of robot learning settings. We'll pre-train this policy with imitation learning. This will be our base policy. This policy will use diffusion. And the first key idea is that we're going to, instead of training the diffusion policy with RL, we're actually going to have a separate edit policy that's smaller, that's going to use a Gaussian distribution, and it's going to edit the actions of the base policy. And because this edit policy will be a Gaussian distribution, it means that we can fairly easily optimize it to maximize Q functions. And because this edits on top of the diffusion policy, it means that the combination of the base policy and the edit policy will be quite expressive. So this is good, and the base diffusion policy will be trained on imitation learning on all of the successes. So that should be quite stable. So that's the first key idea. Now, on its own, this idea may not be kind of a stable RL algorithm. And in particular, we'll see the typical issues that we see with RL, where an edit policy that's optimized to maximize Q values naturally is going to lag behind the Q function, because as you update the Q function, the edit policy won't be automatically updated. And you can also see scenarios where the edit policy might collapse. It might kind of over-optimize the Q values. It might have kind of struggle with the non-stationarity of maximizing Q values and so forth. And these are basically kind of typical challenges that you see in reinforcement learning. So with that, this is kind of only our first key idea. We introduce a second key idea that can address those challenges. And in particular, what we'll do is, in addition to having this edit policy, we'll also sample actions and pick actions that maximize the Q values of the latest Q function. And in particular, what this looks like is we'll sample multiple actions from our base diffusion policy that's trained with imitation. Then we'll sample edits on top of those actions from our edit policy. And so we'll have actions from the base policy, edited actions from the edit policy. And then from these samples, we'll pick the action with the highest Q value. And what this means is that because we're picking for things from the highest Q value, we'll reduce lag with the Q function, because we'll be having this kind of on-the-fly Q maximization step as we are rolling out the policy. And second, it means that if the edit policy does collapse or does kind of have some issues, or it's lagging or something like that, we're still going to be sampling actions from the base policy. And so if these have higher Q values, then it will be, our algorithm will be kind of more resilient to issues in the edit policy. Now, one like kind of final important note with this sort of on-the-fly Q maximization is that this is how we're going to be sampling actions when we're actually rolling out our policy. But there's also a question of, when we're fitting a Q pi with our Bellman update, how do we pick actions A prime in the ladder, in the kind of the right-hand side of the Bellman backup? And because this is how we're sampling actions for a policy, we should also actually use this process to pick actions A prime in the Bellman backup. And we find that this can be actually using this policy that we're going to be sampling from naturally actually helps quite a bit empirically as well. Cool, so that's kind of the key idea of the algorithm. We'll have a diffusion policy that's trained with imitation learning, an edit policy that's a Gaussian policy that maximizes Q, And then we'll use this kind of on-the-fly sampling both when we roll out the policy as well as when we sample actions in the Bellman backup. Cool. So we ran experiments on 12 different benchmarks that have offline data sets so we can do this sort of kind of pre-training and fine-tuning setup. These range from kind of simpler tasks to actually fairly precise tasks like threading, to longer tasks like ant maze, and these dexterous like five-fingered hand tasks. Everything will have sparse like 0-1 rewards, and for now we'll be looking at low-dimensional observations rather than image observations. We selected comparisons that we thought would kind of be the kind of most representative and strongest for kind of offline to online RL. First, we'll compare to RLPD, which is the most efficient RL fine-tuning method that I'm aware of. It's super, super efficient and quite impressive, although it uses a Gaussian policy. We'll also compare to IDQL, which is very similar to the algorithm we saw in the batch online setting, where we are sampling from the diffusion policy and taking the highest value action on the fly. And then lastly, we'll also compare to two different approaches that use diffusion guidance using a Q function. So basically another way to train, to do RL fine-tuning with diffusion. Cool. So here's a snapshot of some of the main results. And our method is shown in orange. We call it expressive policy optimization, or EXPO, in orange. And what we see is that compared to state-of-the-art methods, first we see that it's quite data efficient. So we see that it's able to learn very quickly and get to high performance quite quickly. Second, we found that actually it's like generally quite stable. The learning curves are fairly consistent across different seeds, which is really encouraging to see and something that you want to see when you're going to apply it to real-world systems. And the last thing that's really nice is it has a very high asymptotic performance. So even in cases where RLPD seem to be converging prematurely, we see that we're able to converge on many environments to the maximum performance. Now, it is also worth highlighting that in some environments, specifically this relocate binary task that we tried, it doesn't always work beautifully. And a defining factor that we found in these cases is that if you need significant exploration beyond the offline data set, in order to kind of visit like vastly new parts of the state space, this algorithm is not a great choice. It's more a good choice when you want to kind of improve an imitation learning policy to have higher performance. Cool. And then we also looked at different components of key components of the method and how this contributes to performance. First, if we include like the on-the-fly maximization and in the policy rollouts and in the Bellman backups, but we don't use an edit policy, we see the performance in gray is a lot lower than the performance of including an edit policy. So that seems to be kind of a fairly important component, and this edit policy allows us to more effectively maximize value. And then second, we could use an edit policy and use the on-the-fly policy at test time, but not use it in the Bellman backup. And we see that in some cases, it's not too important to include it in the Bellman backup, but in other cases, we see a really significant improvement from including it in the Bellman backup. And so that also kind of validates that particular design choice. Cool. And then I think the last plot that I have is looking at how imitation learning performance translates to RL fine-tuning performance. And to test this, we evaluated with different offline dataset sizes, different demonstration dataset sizes, and looked at the performance of imitation learning versus the performance after doing RL fine-tuning. And what we see is that at least on this kind of one environment, we see that kind of as you increase the data set size, imitation learning performance improves, but RL performance also improves. And we can translate around like a return of around kind of, 0.35-ish from imitation learning to a return of nearly 1.0 normalized after doing the RL process, which is quite encouraging. And we see this kind of generally like a reliable improvement from the imitation learning performance to the RL performance. Great. So to summarize, EXPO is a kind of stable and efficient RL fine-tuning method that's specifically for diffusion policies. And it has these two key components. One is an edit policy on top of the diffusion policy. And the second is that it does this on-the-fly value maximization at test time and in the Bellman backups. There's still lots of work to do to scale this to large models and to real robots. So those are some things that we're planning to do next. The other thing that I'll mention is that we put this paper in archive, but haven't quite released the code yet, but we're planning to release the code hopefully within the next week or so. Great. With that, I'd like to highlight Perry and Suvir, especially Perry, who led both of the projects that I talked about today, and happy to take questions.
Um, so yeah, questions. Yeah.
Was wondering, I don't know if you can hear me, but I was wondering.
Maybe we can send a mic.
Clarification. Deal with the images that are flashed up to
The question is, what's your expectation when you scale it to images from the low dimensional states?
Yeah, so for the first algorithm we did actually do experiments with images, and like the real robot was with images. For the second one, we haven't yet done it with image observations, and my expectation is pretty positive. I don't think that there's anything in the algorithm that like needs to be done with states. So yeah, pretty optimistic there, especially because the base diffusion policy is just trained with an imitation learning loss. And then the edit policy on top of that can be fairly lightweight. I think that there would be a design choice with regard to like that edit policy might want to reuse visual features from the base policy. And so there's kind of some design choices there for how to design that. But yeah, overall fairly optimistic.
Any other questions? Yeah.
Do you think that online RLC, we should have something as specialized exploration methods that gave us maybe just not like rolling out policy, but giving us more kind of information about the world to update faster?
Did you get the question, or I can
No, it'd be
repeat?
great if you can repeat it. Thanks.
Yeah, so the question is for the batch online setting when you're collecting data in the real world for exploration. Do you think there should be any like specialized exploration method rather than just rolling out the policies that could give more information about the real world?
Yeah, this is a great question. I think it makes sense to be quite intentional about exploration. And one thing I actually didn't talk about that we studied in the paper is we looked at using temporally correlated noise when collecting data rather than just like kind of sampling at random. And we found that there were scenarios where temporally correlated noise is helpful. We also have looked at in another paper a setting that is trying to explore kind of specifically in like add noise in a way that kind of leads you to kind of with kind of learned noise that will lead you to things that look more like the demonstrations, or add more noise if you're deviating more from the demonstrations. And so, yeah, I think there's a lot to explore there. And especially in this batch online setting, like being intentional about how the data is sampled makes a lot of sense. Overall, I think that using the demonstrations as a signal, as a supervision signal to guide exploration makes a lot of sense, because it is like it has a lot of information about what to do. But yeah, a lot of interesting things to explore there.
Does that answer your question? I had a follow-up on this. So, like, when you're exploring in the real world, like online, do you need to take into account like any safety considerations? Because like just even rolling out of the policy can lead to like a weird, unsafe thing. Maybe you might have seen that. You might not have seen that in the domain that you were trying, but in say autonomous driving or somewhere else, rolling out of policies itself sometimes dangerous.
Yeah, absolutely. So, yeah, definitely safety considerations are really important. And even for like these like robot arms that I work with regularly, there are safety considerations both with regard to damaging the environment that they're in, hurting themselves, and also potentially like hitting a human, for example. And there's like various precautions that you can take to like well, for a lot of tasks, there are various precautions you can take to, for example, not have a human in the workspace. That's like kind of a very simple one if the task doesn't require it. You could also, there are hardware limitations that you can put to restrict the amount of kind of torque or force that you can apply depending on the task. Now, there are some tasks where you have to apply a lot of torque or force to complete the task, so that for those tasks is not generally applicable. And then lastly, there's also like e-stops and other kind of ways in which a human can, if they're monitoring exploration, can intervene. So there are like various things you can put in place. At the same time, I think that certainly more research on this is welcome, and it's a really hard problem because I think that there are many ways to do something unsafe beyond just applying a lot of force. Like, for example, if you like accidentally drop a water glass on the floor, that's something that's potentially unsafe. And so it's not something that you can just hard code. It's probably something that at the end of the day needs to be learned in some way or another.
Yep, that makes sense. Yeah, I think we are above time.